This topic is finding a limit of a rational function at a removable discontinuity. So rational functions mean that we're dealing with fractions. So again, we can evaluate limits using tables, graphs, or we want to try to do it by hand algebraically. And that is exactly what we're reviewing, evaluating limits algebraically. If you remember, if we have a polynomial, rational, or a radical function, to evaluate that limit at a point, first thing you should do is try plugging that point directly in. That's called direct substitution. If direct substitution works, if you get a number, that's the number. If you get 0 over 0, that's indeterminate form. Again, you're dividing by 0, so that means the function is not defined at that point. But with limits, it doesn't matter what happens at that point, it matters what happens near that point. So when you get 0 over 0, it's indeterminate. That does not mean the limit does not exist. That just means you have to do something else. In particular, in this case, for this example, we're going to be looking at rational functions, functions with fractions of them. When we get 0 out of 0, or 0 over 0, what is the trick? We want to try to factor and simplify. If it's a compound fraction, get rid of the compound fraction first by multiplying every term by the LCD, make it into a single factor, but then you want to factor everything and simplify, and then we're going to plug in the substitution directly into the simplified version of the fraction instead of the original version of the fraction. So let's go ahead and give this a try. The first function says, find the following limit. The limit as x approaches 0 of the function 4x over 4x cubed minus x squared plus 4x. First thing we always try to do is just direct substitution. So anywhere I see an x, I'll plug in a 0. In the numerator, I'd have 4 times 0. In the denominator, I'd have 4 times 0 cubed minus 0 squared plus 4 times 0. Okay? Notice in the numerator, 4 times 0 is 0, and in the denominator, if I simplify, I get 0 as well. Again, this is indeterminate form. What that tells me is the function does not exist at that point, but with limits, it doesn't matter what happens at that point, it only matters what happens near that point, so let's try a different technique. Let's look back at that original function, 4x all over 4x cubed minus x squared plus 4x. One thing I notice in the denominator is I have a common factor of x. So in the numerator I'd have 4x, and in that denominator I could actually factor out that x. If I factor out that x, what would be left would be that'd be a 4x squared minus x plus 4. Notice now in both the numerator and denominator I have a factor of x, which simplifies. So in the numerator, I would be left with a 4, and in the denominator, I'd have a 4x squared minus x plus 4. So these functions are absolutely identical because we have our equal signs here, right? We've proven that they're absolutely identical everywhere except at x equals 0, but because this is a limit, what the limit allows us to do, we don't care what happens at the point, near the point, what we could say is instead of finding the limit at x approaches 0 of the difficult function, I'm actually going to find the limit as x approaches 0 of the simplified function instead. So this is equivalent to, we need our equal signs, the limit as x approaches 0 of, again, I'm going to plug this into the simplified version of the function, 4 over 4x squared minus x plus 4. Let's try that direct substitution method again. So that'd be 4 over 4 times 0 squared minus 0 plus 4. In the numerator, I'm ending up with a 4. In the denominator, I have a 4, so that simplifies to the value of 1. So now we were actually able to evaluate the limit because what we did first was factor and simplify. So that's our trick on the problem. If we get that indeterminate form, it doesn't mean the limit doesn't exist. Try factoring and simplifying first, then evaluate the limit on the simplified version of the function to get your answer. Let's try that again. Problem number 2, find the following limit. The limit as x approaches 1 of x minus 1 over x squared minus 1. Notice if I try direct substitution in the numerator, I'd have 0 minus, we're evaluating this at 1, right? So I would have 1 minus 1, and then in the denominator I'd have 1 squared minus 1. So in the numerator I have 0, in the denominator I have 0. Again, that's indeterminate form. All that indicates is that the function does not exist at that point. It does not indicate that the limit does not exist. So what do I want to try to do? Let's look at that original rational function, x minus 1 over x squared minus 1, and see if we can factor and simplify that. Well, the numerator is already a factor, x minus 1. The denominator is x squared minus 1, which is a difference of squares, so that factors into x plus 1 times x minus 1. Notice now, in the numerator I have a factor of x minus 1, in the denominator I have a factor of x minus 1, so those simplify to a 1. So the simplified version would be 1 in the numerator and an x plus 1 in the denominator. So instead of finding the limit as x approaches 1 of the original function, I'm going to find the limit as x approaches 1 of that simplified function instead. So I know this is equal to the limit as x approaches 1 of, now I'm going to plug in that simplified function, the 1 over x plus 1. We'll try the direct substitution method again. This would be 1 over 1 plus 1, which would be equivalent to 1/2. So that should be our answer of 1/2. If you wanted to verify this another way, we could always do a table of values approaching 1 from the left and from the right, or we could graph this using a graphing app, something like Desmos, to verify it graphically as well. Okay. Let's try one more here. It says find the following limit. The limit as t approaches 0 of the quantity -4 plus t squared minus 16 all over t. Always try direct substitution first. So this would be -4 plus 0 quantity squared minus 16 all over 0. -4 squared is 16. 16 minus 16 is 0. In the denominator we have 0. So that's indeterminate form. Again, that just indicates that the function does not exist at that point. It does not indicate that the limit does not exist. So let's look at the original function, see if we can simplify it at all. -4 plus t squared minus 16 all over t was our original function. I'm going to go ahead and FOIL out that top. So if you did -4 plus t times a -4 plus t, if I FOILed that out, what would I get? Well, -4 times -4 is a positive 16. Then I'd have minus 4t, minus 4t, and then I'd have plus t squared. I'm going to go ahead and write that in descending order and combine like terms. So I'd have t squared minus 8t plus 16. So in the numerator, I have t squared minus 8t plus 16. Again, all I did was FOIL out that first part. So I still have that minus 16 there. And again, that minus 16 is right there. And then in the denominator, we have a t. Notice we have a positive 16 and a negative 16 in the numerator. So it looks like I have t squared minus 8t in the numerator, and I have a t in the denominator. Looks like we can keep on going because I have a t as a common factor in the numerator. So if I factor that out, it would be t times t minus 8. And in the denominator, we have a t. Now that I have common factors, I can go ahead and simplify those common factors into a 1, and I'm left with simply t minus 8. So my original function was the quantity -4 plus t squared minus 16 all over t. The simplified version of that is t minus 8. So instead of evaluating the limit into the difficult function, we're actually going to evaluate the limit into the simplified function. So we know that this limit right here is equivalent to the limit as t approaches 0 of t minus 8. Now that we're finding a more simple limit, we can just go ahead and try to directly evaluate. So that would be 0 minus 8, which gives us a value of -8. And there's my final answer right there, -8. So what's the best way to evaluate limits when it says find the following limit algebraically? Plug in the number and see what happens. If you get 0 over 0, it's indeterminate form. That just means the function exists. That does not mean the limit does not exist. So you do need to try to manipulate it. When you have fractions, one of the easiest things to try to do is to factor and simplify. Once you factor and simplify, plug the limit into the simplified version of the function instead of the original version. When you plug it into the simplified version and get an answer, that answer is your answer. I hope that helps.